Hey Dre, so I wanted to help you out with your heart rate variability data, and some of the things that you said, I kind of led me to believe that it might help you out to try to break down an understanding and interpretation of heart rate variability and heart rate data in general. I'm sure you've read some of it, but really 2 months, it's just really not enough time to get a good conceptualization of it if you're trying to teach it to yourself. I mean, a lot of the stuff that you will find online reading articles and stuff is going to be pretty high level stuff, and really there's only a few basic things that you need to know that'll help out the interpretation of heart rate variability data that will kind of make it easier to interpret. One problem is that I noticed, and I'll come back to this again later, is from the data you sent me, it looks like it already does a lot of the processing for software directly from heart rate. It would actually, if you could, I don't know, I'll have to mess with your software later, but it might be preferable if there was any way you could get it to just give you raw heart rate data, or just show you like interbeat intervals, in the form of numbers, and then you could have more freedom to do with that data what you will. Right now it looks like it's just giving you straight low frequency power, which is very limited. I mean, it seems very black boxish. So you just kind of are just taking the heart rate data and automatically interpreting it. It sounds like they're even already doing the fast Fourier transformation. And some of the numbers don't really make sense to me. It could be because of my limited understanding of it. Like I said, I'm definitely not an expert in this area. I feel like I kind of have a good understanding and conceptualization of it, but I really don't know very much about interpretation of the low frequency band of heart rate variability. I know that it is related to changes in blood pressure, and some people have looked at it in relation to cognitive workload. In fact, you might know more about that than me since you're working with it. You might have looked at a few articles relating low frequency heart rate variability to cognitive workload, but most of my familiarity is with respiratory sinus arrhythmia, which is the high frequency band of heart rate variability. So I wanted to start with one of the probably some of the most confusing things about understanding heart rate variability is that you have all these different graphs and different ways of looking at heart rate. I mean, it starts with this, which is the symbol that everyone knows when they think of heart rate. But then once you try to convert that into heart rate variability, it gets a little bit more confusing because the axes change, and what the lines represent no longer mean the same things, and it's easy to get them confused. And so when you said something about how not understanding how something that samples at 32 times per second or 32 hertz could calculate interbeat intervals, it seems a little bit like you might be misinterpreting the way these things work. And so I figured I'd just start from the ground up, but I'm only going to cover the basic things that you need for understanding and interpretation. The reason I chose to do a video is because I just feel like it's easier for me to talk about it and show it on a whiteboard where I can draw things than to try to type it out in a really long email or something like that. So starting out, when you have a device that's measuring heart rate, like you have, about the electrode placement and things like that, the raw data is just measuring electrical activity on the y-axis and time on the x-axis. And most of these things that we're going to be looking at will have time on the x-axis, but the y-axis will change. So what we see with a heart rate data here are just changes in electrical activity that are associated with the beating of the heart. There's the signal for depolarization and P wave, and then I can't remember all the technical terms, but that's not really important for your purposes. Mostly, what's important is when you talk about your device sampling at 32 hertz or 32 times per second, that means that every second it's sampling 32 times, right? And you're saying you didn't really understand how it could get IBI values from that as well. That's because at 32 times per second is picking up this level of electrical activity. So it will be able to sense these changes in electrical activity, and thus it would be able to capture actual heart rate. And since it's plotting it over time, it will be able to capture this, what we call the interbeat interval, or IBI. That device should have no problem with capturing. I mean, 32 samples per second is plenty for any frequency of heart rate variability that you want to look at. So, how do we look at this and reinterpret it into a measure of heart rate variability? Well, heart rate variability is just going to be changes in these IBI durations. So an IBI is just a unit of time that's in between peak heart rate, electrical activity. So this might be 3 seconds, and this one might be 3.5 seconds, and so on and so forth. And your heart rate varies over time as a function of a lot of different physiological processes that are happening in your body. The high frequency band, we call it respiratory sinus arrhythmia because it fluctuates with your breathing. So as I inhale, my heart rate tends to pick up slightly, and then as I exhale, it slows down slightly. Or I might have that backwards. No, I think it's right. I think it's as you inhale, it increases slightly, and as you exhale, it decreases slightly. So how that is related to workload is in that that variability, so the changes in the interbeat intervals decreases. So your heart rate becomes more stable over time as your cognitive workload increases. And I'm not confident enough to really know the theoretical reasons behind why this happens. Now, regarding the low frequency band, so when we talk about high frequency and low frequency, we need to switch graphs. So I'm going to erase this one, and I'm going to move on to another graph. All right, so we have all the interbeat interval data. You've collected your sample, and now it's time to interpret this into changes in heart rate over time. You derive heart rate from looking at just the peak-to-peak intervals or the interbeat intervals, but the way that you graphically display that becomes it's different, but it can be confusing because it looks similar. So now on the x-axis, instead of having electrical activity, on the y-axis, instead of having electrical activity, now we have heart rate. Okay, so now we have the collection of interbeat intervals. A higher heart rate, I'll just write HR for short. So higher values on this y-axis will indicate smaller interbeat intervals, right? Because as your heart rate increases, the time in between interbeat intervals decreases. And on the x-axis, we have time. So I'm going to break it up into the bands, because this will make it a little bit more clear. When we're talking about high frequency heart rate variability, we're talking about variability that happens at 0.15 to 0.4 hertz, or basically that's heart rate variability that occurs between 2.5 and 7 seconds. So what that means is we're just narrowing the window of our time when we're looking at heart rate variability over a period of 3 minutes or whatever. We're just narrowing our window to look at variations that occur within a specific time frame. If we wanted to upgrade that to low frequency heart rate variability, we just widen that window. So now we're looking at heart rate variability that occurs between 7 seconds and 25 seconds for low frequency heart rate variability. Now to show that graphically, so here we have time, and on the y-axis we have your heart rate. So let's just do it in 1 second intervals for time. All right, so as I said, heart rate variability happens or average around 4 seconds in 4 second windows. So let me break these up by 4 second windows. All right, so about that. So if we look within these 4 second windows, we'll see your heart rate increases, and then it decreases. And then it increases, and then it decreases. Now, if we're looking at the trend over time, and we want to capture that low frequency heart rate variability, we're going to see that this wave, this variation, does not stay stable. So we might see like a gradual decrease and then a gradual increase. And I know these are not proportionate. So what you see here is when we talk about different frequencies of heart rate variability, it's what that means is that there are two curves, okay? So the high frequency, we have these quick oscillations in heart rate. As I'm inhaling, my heart rate is increasing, and as I'm exhaling, my heart rate is decreasing. And then for the low frequency, we have these slower waves that go like this. All right, so it's a curve within a curve. So as time passes, I'm inhaling, my heart rate's increasing, and then it's decreasing. And then also, because my blood pressure is changing, my overall heart rate is also decreasing and then increasing. So it's just a matter of looking at time windows and looking at the curves within the curves. And hopefully that makes sense. And as I said, my scale is all wrong here, but just so you can get an understanding. So how do we break this up into its separate bands? Well, you have to do what's called a fast Fourier transformation. And I'm not sure, but it looks like your software is already doing that. But the first thing you have to do is, so we have to switch to a third type of graph, okay? And here's where I get a little bit fuzzy in the interpretation, so I might be giving you some wrong data. I'm going to read up on it a little bit more and then get back to you. But now the axes all change. It's no longer over time, because this becomes a three-dimensional graph when we look at fast Fourier transformations. And don't let that name, intimidate you or anything like that. It's just a fancy word for a relatively simple process. All right, so this is the third transformation that happens. So we started out with raw heartbeat data that just shows electrical activity on the y-axis and then time on the x-axis. And then we calculated the interbeat intervals to try to get heart rate. And then we plotted a new graph. And I might not have made this clear, but let's pretend that this is still heart rate. So the heart rate looks like this. This graphically has nothing to do with the electrical activity waves that we saw in the previous graph, right? So this is just a change in interbeat intervals. As I said, so like as you get higher heart rate, these are lower interbeat intervals. So what this is going to look like, I'm going to draw underneath it what the electrical activity would look like. So here we're going to see, so as it's really high, we're going to see really short interbeat intervals, and then as it decreases, we're going to see longer interbeat intervals. And then as it increases, we'll see shorter interbeat intervals. And then we'll see longer interbeat intervals. And my graph degraded over time as usual. So this is what the electrical activity would look like, because we can still use the same x-axis because we're still looking at time as our x-axis, but now this is just an interpretation of these interbeat intervals. So short interbeat intervals over time will be calculated into higher heart rate. Now the question, one thing that becomes difficult with this is, so your heart beats once every couple seconds or something like that. How can you calculate changing heart rate variability when you're only getting a couple of beats every few seconds? And that's one of these things, is that to really get good heart rate variability, you can't measure it in real time. We cannot measure heart rate variability or heart, we can get interbeat intervals in real time, but interpreting that into a form of heart rate, you have to have at least a 2-minute window, I believe is what is used. And it sounds like you guys are using 3-minute windows, which is fine, but really you want a longer task, because to reliably get interbeat heart rate variability, you need to have these 2-minute windows with some bit of overlap in between them. I can go into more detail on that later, but again, that's an area I'm kind of fuzzy on right now. So right here I have an interbeat interval, but obviously I couldn't directly calculate heart rate from that, because it would be nice if it was lawfully related that, if I know I have a 2.3 second interbeat interval in between two heartbeats, it would be nice to know that that means my heart rate is going to be this. But despite, so we have the heart rate variability because of respiration, you have heart rate variability because of blood pressure, but you also just have random oscillations. It's not a perfect clock. Your heart doesn't keep a perfect clock. So there's going to be variability that's not associated with either of those things. It's just natural variability, or variability because of factors that we can't exactly measure right now. So what we can do is that we get 2 minutes worth of heart rate, and then we can calculate average by looking at this whole sample. We can like average the interbeat intervals on like an overlapping fashion, and that kind of gives us the heart rate for this chunk of time. You know, so we get little plots of interbeat intervals which are averaged, and that gives us heart rate over time. Anyway, so then interpreting that into a measure of power or heart rate variability. Again, like I said, now we have to switch graphs. All right, so this is going to be a three-dimensional graph, and you might have talked about that. I know we talked about fast Fourier transformations in perception, but your experience with them might be limited. My experience with them is very limited too. But just to go into it now, on the y-axis, we have power, and on the x-axis, we have frequency. And so what this means is that this is going to range from, this is going to have capture both power of low frequency heart rate variability and high frequency heart rate variability. So the frequency here will be, so we'll just arbitrarily label this as 0.04, and then 0.15, and then 0.4 up here. So any power that we see in this window here will be because of low frequency heart rate variability, and any that we see in this window here will be because of high frequency heart rate variability. What I think, and I'm not sure, but I'm pretty sure an increase in power means an increase in variability. Okay? So when you see higher spikes, that means that there was greater heart rate variability for that specific time frame. Now, how do we show time on this graph? As I said, this is a three-dimensional graph. And so to show time, you have to draw multiple lines. And the fast Fourier transformation uses multiple lines to draw time. So when we're looking at, so we'll be looking at multiple lines which show changes in power over time. So when you look at a full spectral analysis, what you'll probably see is something that looks kind of like this. Probably. So this will be the first unit of time, and then you add in more lines as time progresses. So, and obviously they're going to look better than what I'm drawing here, but it's going to look something similar to this. One thing about these types of three-dimensional graphs is that you kind of have to get a feel for changing values on the y-axis, because this would seem to imply that power is changing over time. That's not really, I mean, it is changing over time, but it's not increasing. It's not like as each unit of time it goes up that the power actually increases. It's kind of, you gotta kind of imagine there being some depth to it. So you will see changes. So you see, like, there might be a little bit of overlap here, so there's a decrease in power, and a little bit of overlap here. So the lines will overlap with each other slightly, showing how actual power changes over time. And then basically, and here's where I get fuzzy. Like I said, I haven't analyzed heart rate variability data in a really long time, and when it gets to this point, I'm going to read a little bit, and I'm going to write up some instructions and send them to you. But from here, this kind of just gives you, the point of this video is to just kind of give you a conceptualization of how we get from measuring the electrical activity of the heart to what we see when we look at a spectral analysis. All right? So hopefully that was clear. I'm trying to think if there's any other points I wanted to cover. Obviously, when you're looking at like the power represented within this window would be high frequency. So power within this window would be low frequency. So you would be mostly focused on changes of power within this point. I did look at your data, and I thought it was odd because the way it's presented, as I said, it looks like it already does the analysis. It would be nicer if it just gave you the raw IBI data. But it looks like it's already done the fast Fourier analysis and calculated power, but it gives you power for each unit of time for every freaking sample that the device takes, which is really weird. It's going to be hard to interpret. Another thing, and like I said, I'll go over this in my email, but you definitely, I'm not sure if you just didn't use event markers or if the device doesn't have a method of marking events, but to use it, you definitely need some sort of event marker. I mean, I guess you could record, but that gets really messy because usually events are going to be, you want them to be as discrete and as exact as possible because you want You want to be able to see how the gradual changes occur after an event happens. All right, so I will start writing up the email now. I'll probably post this to YouTube or something.